Atwood's machine was proposed by George Atwood, a British pastor, mathematician, and physicist, in his 1784 paper on the linear motion and rotation of objects, which was used to measure acceleration and verify the law of motion. As you can see, Atwood's machine is made up by one stable pulley, one iron string, and two masses, which the mass 1 is heavier than mass 2, so the string will slide to the right side. So now let's look up some Atwood's machines in the history. The four examples below shows the clock mechanism controlled by the second pendulum, and the vertical scale showed the distance of fall. The only one still in operation is the example at Marietta College, made by Pixie of Paris in the 1830s. It was listed at 800 francs, about $200, in the 1849 Pixie catalog. The corner of knowledge adorns its top. The examples from Mississippi and the National Museum of American History of the Smithsonian Institution were also made by Pixie. The Smithsonian machine was originally at the United States Military Academy at West Point. Today, I'm going to show you how to calculate the acceleration of the pulley by using the Newton's second law. First of all, Newton's second law states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of this net force, in the same direction as net force, inversely proportional to the mass of the object, also as A equals to F net divided by m. When doing problems on Atwood's machine, we will make three assumptions. First, the pulleys have no mass. Second, the string have no mass. Third, there is no friction between the iron string and pulley. For the mass 1, the forces on it are gravitational force and tension force. Thus, the net force on the mass 1 can be calculated by using tension force minus the gravitational force. Since the formula of gravitational force is mg, also the net force can be calculated by using Newton's second law, F net equals to ma. Therefore, we can conclude the equation m1a equals to t minus by m1g. Just to clarify, the direction of acceleration 1 is upward.
Can I stay a bit longer?
Back to mass 2.
Stay forever.
The two forces exerted on it are gravitational force and tension force, which can be defined as T minus by m2g. So we can also conclude the equation m2a equals T minus by m2g. When we straighten this out, we will get the free body diagram like this. By using the equation of A equals to F net divided by m, we will get the equation of A equals to m2g minus by m1g divided by m1 plus m2. Basically, by knowing the mass of two objects, we can get the acceleration by using Newton's second law. For example, we can use the mass 1 equals to 220 kilograms and mass 2 equals to 30 kilograms equation that we get to calculate the acceleration. So the acceleration will equals to 30 kilograms times by 9.81 minus by 20 kilograms times by 9.81 divided by 20 kilograms plus 30 kilograms, which will equals to 1.962. So now I'm going to show you what does the real Atwood machine looks like. So when mass 1 and mass 2 are same, the acceleration will equal to 0. When mass 2 is the double of mass 1, the acceleration will be 9.81 m1 divided by 3 m1 equals to 3.27. We can also conclude the equation of tension by using m1a equals to t minus by m1g. We will derive the function of tension, which is g times by 2m1 m2 divided by m1 plus m2. So in conclusion, when mass 1 equals to m2, The machine is in neutral equilibrium regardless of the position of the weights. When m1 does not equal to m2, both masses experience uniform acceleration. We can get the equation by using the Newton's second law, which is A equals to G times by m2 minus by m1 divided by m1 plus m2.